All right, did anyone need Cedric's work again here? We good on that?
I was right, okay.
Okay. And then we think the answer here, we think the slope is 1. Doesn't it look like it? That was a bad picture, but there we go, right? All right, we're going to use that second part of the warm-up as we build a case for what we think the derivative of e to the x is. So there it is again, a better picture. Let's assume that that's the case. And again, if it's not the case, then find a number, look at my picture over here, find a number, a, for which it is the case, okay? Because there is such a number, and we're just going to assume that we found it, and maybe it's e. But if there isn't, then like let e be that number that does the trick, right?
Okay.
I think by saying that you just said that this is true. Am I right?
Yes.
That's really a way of saying what our assumption is, using the definition of the derivative. Yes? You're claiming that y prime of 0 is 1. And by y prime, of course you mean the limit as h goes to 0 of e to the 0 plus h minus e to the 0 over h. Isn't that the definition of the derivative?
Yes.
Yeah, oh, yes. I get that.
Right? F of x plus h
Yeah.
minus f of x over h. So I just want to make sure you're clear about what we've asserted, if we really think that slope is 1 there. Okay, so now we're ready to actually use the definition of the derivative to find the derivative of e to the x. Here we go. Use the definition of the derivative. Agree that that's the definition of the derivative in general, not just for 0, but for any x. Using properties of exponents, the first term in the numerator can be written as e to the x, e to the h. And then using algebra skills, we can factor out e to the x. Notice that e to the x doesn't have an h involved. And so when we factor it out, we can take it all the way outside the limit. And now the only thing at play is this. We're wondering what is the limit of this remaining quantity that doesn't involve an x. It just involves h. And we have already asserted, at least we think, that e is maybe that number that makes that limit come out to be what?
1.
1. You see what we've done there? Some of you already maybe have heard that this is true. But the derivative of e to the x appears to be, or for whatever number has this property, right? Appears to be e to the x. So we just, and so in fact, you might be thinking, doesn't this all hinge on this? On the fact that we made that initial assumption? In some sense, yes, it does. But in some sense, maybe we just call e that number, which does the trick. We know some number must do the trick. For some exponential function, there must be one. So in some ways, this could be a definition of e for us. That e is the number, one more definition for you, that does this trick. But it's really worth stopping and like breathing on and like realizing that this is like an extremely unique property. Yeah.
Does this work for other stuff like 2 to the x, 3 to the x, etc.?
So the answer is like no, because they don't have the slope. The slope of those functions isn't necessarily 1 at x equals 0, right? When you do this, run this, you get something different for this limit, right? But it should be something else exponential maybe. You'd expect the derivative of an exponential is still exponential using this kind of logic. All right, did you fully digest that?
Yes.
It's time for a quote and a picture. E to the x is like the phoenix, man. Because what's the, right? I mean, if you try to, I think we, yeah.
Who is this?
This guy right here.
Jackson, come get your
So, I want to make sure you're clear that the reason that in some sense this is acting Phoenix-like is that I think we asked this question, you know, a month ago or something like that. What's the, take a polynomial, what's the derivative? Well, you get a polynomial at lower order by 1. Take another derivative, what's the 7th derivative of a cubic or something like that? What would be 0? 0 got through quickly and dies, right? But u to the x, what's the derivative of u to the x? What's the second derivative of u to the x? What's the third? What's the 17th derivative of u to the x? Well, it's still u to the x. So you can see that this, the differentiation operator doesn't have any power against u to the x. The other thing that's remarkable is that, like, when you're looking at the function e to the x, notice that, like, what we're saying is, like, if you ask, what's f of x, what's f of 1, it gives you the height on the function. But if you're also asking, like, also, what's the slope there? The answer to that question is also the same answer. So you're like, what's the slope there? And you're like, well, what's the slope at x equals 1, for example? Oh, well,
1.
E, right? And you're like, no, I asked for the slope. No, it's E, right? That's not a mistake. The height is E at x equals 1. The slope is E. What is Miss Caffey talking about over there? You're killing my phoenix. Trying to talk about u to the x over here. All right. E to the x is important. And in fact, I think the way E was introduced to you is a little bit like anticlimactic, I think. And I wish, in some sense, if I were to like reinvent all of the mathematics, for example, it was my job to do that. I would maybe wait until calculus to even mention E. Because the thing you think of E as being special for is because it's like, oh, compound interest, continuous, right?
Yeah, I remember that.
I don't know, that's not very alluring, but the fact that it has this property is just mind-blowing. There is no other function besides the trivial one, y equals 0, that has itself as its own derivative. The reason I'm holding these books is because someday you'll take differential equations, maybe next year, and or maybe in college. So here are 2 differential equations textbooks, and here's the game you play with them, all right? Because I just want to prove to you that e to the x turns out to be like one of the most important functions in your life, okay? So here's the game you play in the differential equations textbook. Open up a page and see if you can find a page that doesn't have E on it. You see an E on there? I didn't do it this time. See it? That is a little tiny italicized E, not a letter.
I see it.
Yeah. See it?
Yeah.
All right, so that's the game. So let's see if do it 10 times, see if you can find a page that's right? I got 2. Play this game with me.
Are we actually playing the game?
No, this is a side game. We're gonna.
Index.
Did you get one?
When you say you can't find an E, do you mean like in the letter or the like E? Like,
Point something.
E to the x, the E actual E function. All right, so let's find some derivatives of E to the x, and of course, just throw them in. Just throw them in mix, right? We got the trig ones. We got to throw in some product and quotient rule. We got everything now, right? Every time we introduce some new derivatives, we got to stir. I win. Right?
Mr. Gates, I got out on my first try.
Yeah, it'll happen. It's just not very often. Now, I will say that any of these problems here, I guarantee you that in the solution.
Wait, are we doing that this year? Okay, that's multivariate.
All right. The look in the textbook game is a side game what we do while we're working on these problems. Okay. No, there are only 2 books here. All right. So help me. How do we walk us through e to the pi x? What are we going to do? Keep in mind that, of course, pi is a constant. So what is the derivative of e to the u? The derivative of e to the u is e to the u times the derivative of u with respect to x. So it's e to the pi x times pi, right? Because that's the derivative of pi x, okay? Chain rule.
Because it's like the ES sign.
It's its own thing.
Yeah.
Who wants this? What do we need here? What do we need?
So it's e to the x times cotangent x plus
E to the x times
cotangent
cotangent x, because that's the derivative of e to the x times cotangent.
plus e to the x over. Wait, why
It's plus.
It's
Negative
plus, but minus
cosecant
plus.
x
Yeah,
cotangent.
yeah, whatever.
What's the derivative of cotangent? I forget.
Negative
Cotangent.
cosecant, negative cosecant.
What is it?
Cosecant.
Negative cosecant.
That's
Negative.
a negative.
No, exactly. Oh, yeah, I see what you're saying. Wait, no, secant squared. Just kidding. Haha.
Yeah, I was
just
gonna say, I
kidding.
thought I heard some people saying cosecant cotangent or something. That's not.
That's
So I think that's good now, and if you wanted to factor out e to the x, you could, but you don't need to. So is it clear that that's the derivative?
Yes.
Okay. This looks like fun. Looks like we got a little chain rule happening, and we got some quotient rules.
What is it?
It's like double flag on the play. You've got plugged in over there, and
Nathan, there's a charging station over there.
there is actually I have a charging station. Anyone wanna? Like I said, if there isn't in the exercises somewhere, I guarantee you that in the solutions to those exercises,
I guess we'll just have to do them all.
you have to do all the problems. Huh? Yeah, it is. I can tell from 20 feet that it's an exercise. Huh?
Wait, this is ill.
It's not a fun game? Yeah, you win. You win. Okay. Who will venture into the deep waters on this one?
I can do like the first part.
Do the first part. Listen, guys. Listen as Derek does the first part. Go ahead.
Square root of x minus x squared,
Bottom.
right? Times cosine e sine to x.
Yeah, e sine x times cosine
Yeah.
x. Because that's the, in parentheses there, that's the derivative of the top. He's right.
Oh, okay, yeah. And then
Using
minus
the chain rule.
Minus
e sine
sin x.
Yeah, minus top.
times, wait, let me think about this. Negative 1. Oh, do I not have to put?
Just make it 1/2 parentheses x minus x squared.
So negative 1/2.
Yeah.
And all over.
Wait.
Yeah.
Oh, true that.
2x. And then
Over
x minus x squared.
square root of x minus x squared.
Yeah.
All right, yeah, and then of course there's some simplification that could be done.
Nope. Just leave it like that.
That's not happening.
You can just square it to get x minus x squared, right?
I don't know.
I'm not doing this.
I might call a camber on this one. Okay. Okay.
No, I got something.
There might be some things you could do. I think there actually might be worth it doing some of this. E to the sine x could be factored out. We've got this certainly can be squared, and we can get rid of the square root. But we've crossed the calculus boundary at least. Is that okay? In terms of, and there's a lot going on there, right? We've got the chain rule, we've got a new derivative, and we got the quotient rule.
Wait, can't you also whatever?
How do we finally, now that we've got e to the x in the mix, let's try and do in general a to the x. All right, well for this we need the power of pre-calculus, okay? A to the x, do you agree that a to the x can be written in this way?
Yes.
Yes.
Do you remember this? That e to the natural log of
Isn't that what they're
something
learning right now?
is us really not doing anything, right? It's just e to the x, it's still a to the x. By the inverse property, right?
Yes.
And then, assuming a is positive, we can drop the power. You remember the up here?
Yes.
ln a to the x is x ln a by the power rule for logs. By the power rule for logs. Notice that we still have not done any calculus yet, okay? I just want to make sure you're clear. We're just rewriting a to the x in a different way. You see, we're like going out of our way. We're really going out of our way to be lazy mathematicians and use a previous result. Like we'd like to force our hand and have e to the x appear somehow. And by, again, well, now this is like e to the pi x. Did you know how to take the derivative of e to the pi x? on that last slide? Well, that's the situation we're in. Keep in mind that a is just a constant. ln a is just a constant, right? So what do we get? We get e to the, in the pi kid situation, it was e to the pi x, wasn't it? Was the derivative. Times pi. So what do we get here? We get e to the x ln a as the derivative. 08 times ln a. Right? It's the same thing as taking the derivative of e to the pi x. We just need to realize that that exponent is just off by ln a.
Why does that?
So this is our, well, we're not done yet here, right? So we have this times ln a, but remember this was just a to the x. Remember this piece here? We started by rewriting it this way. That's just a to the x, the thing that's out front.
Well, we can skip all that now,
Let's
right?
put it in a box. Yeah. Hey guys,
Yes.
let's hear Jack's question.
What if it's ln x?
What if it's ln x? What do you mean?
Like, because ln a is just a constant.
Yeah, you mean if this was like e to the x ln x, then there would be a completely different problem. The thing we're taking the derivative right now is a to the x. But at the end, tomorrow I'd like to take a look at the function like x to the x as well. And that's a whole different ballgame,
That's
right?
e to the x ln.
Yeah, but if it's a constant to the x, if it's some constant to the x, then this is the derivative, right? Now, hey guys, come stay with me. If a happens to be e, then what do we get here? If a happens to be e, then what do we get here? What's the derivative of e to the x? Well, it's e to the x
That's 1.
times ln e, which is 1, right? So works even in the e to the x case. In fact, you could use this formula only, but e to the x is so ubiquitous it's worth a box. It's definitely worth a box. All right, so let's find the equation of the line tangent to this function at x equals 5. No.
Why? What? No.
So we need the usual things. We need the point. It's 5 comma 32, and we need the slope. And for that we need to figure out what the derivative is, though, right? So what is the derivative? What's y prime?
2 to the x times ln2.
2 to the x ln2 apparently. And then if we put in 5, we get 32 ln2 as the slope. And I think we're ready to write the equation of the tangent line. It's y equals 32 plus 32 ln2 is the slope, I guess, times x minus 5. Okay? Just point slope form, right?
Oh, yeah, 5. Okay. I got it.
Any other thoughts there? Yeah, I just want to give you a tangent line problem too. I mean, everything's in the mix now. Like, we got these new derivatives, we can ask you all the things we've always been asking you now with these new problems. Let's take some more. I don't know, take a second to do these.
Oh. Alright, I can do this.
Notice here the instructions are find y double prime.
Just the second part, right? No, we can't do it. Hey, Sean, how about you do the second part? I do the first part.
Please, one hint I'll give you is use any shortcuts you know to make your work better or easier or faster.
I'm gonna not do it instead just do B.
3, 5, 2, is that it?
I want to make this one.
That's it. I'm gonna do this.
Just like something I don't on the test. Why is it? I just kind of low or high speed. What should I do? Wait, so what do you 3 to 2x times ln and 3? Oh no, but what it would be, isn't 3 to 2x the same as 9 times
Yeah, because now we have to do all the things with a to the x. Chain rule, product rule.
yeah, because 3 to 2x is 9 times 3 to the x.
Wait, why don't we just change
3 to the cubic. 2 times 3 to the x.
The cubic times times of the speed. But it's chain rule, so you have to multiply. No, 3 to 2x. 3 to 2x is 9x. 9 to x. It's right 9 to 2x. Camera distracts Jackson.
No, we don't distract the other. This one is like turn off.
Yeah. You gotta hear that. No, it's Derek. I'm just gonna call it easy.
Oh, is that easy? Oh, something I've already
Derek, you know why I love you so much? I love you more than both Camber and Shimon combined. Because during lunch today, people were telling me that the homework was homework 4. And I was like, wait a second, I can do homework 4. And then so I called Shimon, and they were like, wait, why do you and then I called Camber, and wait, why do you? And then I called Derek. No, Corinne was the last person. Corinne was actually the last person. Oh, okay. No offense, Corinne. No, you wouldn't understand. You're not sitting here.
But I checked that sometimes this box.
Where's 99?
Yeah.
That's A. What's this A?
Did x to the e to the x, the first derivative? Yeah, so it would be e to the
Alright.
x times 1 and then
Let's
x times
let's struggle through this here.
E to the x plus x e to the x. So e to the x times 1 minus x.
All right, so talk us
Yeah, that.
talk us through this here, if you will. Who will help us with the first one here?
I can.
Yeah, do you want to do the first one?
Sure.
Okay, what do we do?
Okay, so first I simplified it to 9 to the x. Because that just makes it a whole lot easier to deal with. And then you just...
I heard Jack saying
How'd
that
you
too.
figure that out, Jackson? All of myself with no help from outside resources. And then I just put it into the little formula that we have, so it's 9x times ln 9.
That's good. For those who did it the other way, how does that feel? Is it actually the same answer? F prime of x equals 3 times 2 to the x ln 3 times 2. So is that the same thing as this? Well, what's 3 to the 2x? Apparently that's 9 to the x. And what's ln of 3 times 2? The power rule, right?
Oh, yeah.
Excuse me, the logarithm power rule.
Yeah, ln of 3 squared.
Is ln 9, right?
Yeah.
So it is the same. Okay. I don't know that there are any like slick shortcuts on this one, so someone just walk us through this one here. You want Shivani? Yeah, go for it.
3x squared times 4 to the x plus x to the third times 4 to the x
We haven't done the derivative of ln x. Maybe we'll do that next. Be good. All right. So this is good. I don't know. I don't think we need to clean that up. Actually, it's good. All right. This one looks like fun. Y prime equals first times the derivative of the second plus second times the derivative of the first. And then y double prime, I like this one. In fact, I'd love to do y triple prime. What do you see happening? I mean, you're going to have the same, this is what appeared here. So we get the same derivative, plus e to the x, plus e to the x, right? Like this derivative happens again. So you can imagine, what do you think the fifth derivative is?
Yeah, I don't know. You just add 2 e's. Or add, add 2 e to the x's.
What's the fifth derivative? If the second derivative is x e to the x plus 2 e to the x,
X equals to x plus 5.
maybe it's plus 5 e to the x or something? Proof by induction. All right. Yeah, prove that the nth derivative is e to the, you know what I mean? A little proof by induction, okay? Okay. Who can help here? Someone other than this table.
Wow.
Ashley, thank you. Go ahead. Listen. It's Ashley time. What do you got?
2 to the x times 2 to the x ln 2 plus 2 to the x times 3 to the x ln 2.
Okay. That's y prime. Oh. We're supposed to do y double prime too. Does anyone have any tips for us? Tips and tricks. Okay, Canberra, I'm willing to listen.
Yay. Well, I get it that you can simplify 3 to the x times 2 to the x to 6 to the x. And then if you find the...
Wait. I need to go back to algebra 1 for a second. Is that right?
That's not what I meant. I meant you can simplify what the derivative is into 6 to the x times natural log of 6, eventually.
Well, if this comes out to be 6 to the x ln 6, I think maybe you have a case for why this is 6 to the
Oh wait,
x.
then I was right?
Don't let them boo you.
Oh.
I didn't say anything.
Yeah.
Or when you solve the log, or not the log, the derivative of like ln 2, you have to use like the inverse of the derivative of
Oh yeah, we haven't gotten there yet, but you're yeah.
I was right.
I like how you're thinking. So yeah, why is this 6 to the x? Algebra 1 lesson, quick, someone help me out here. What's the algebra 1 lesson on why we can say this?
Because of exponent rules.
Because of exponent rules. What is this? Is 2 times 3 to the x. And how do you do that? 2 times 3 to the x is 2 to the x, 3 to the x. Right?
Wait, so Cameron was right?
Canberra was right, yeah. Alright, so that's y prime. That makes y double prime quite a bit easier to find now. Because this is just like a constant times 6 to the x. So what do you get? You get 6 to the x ln 6 times ln 6. Right? ln 6 squared, if you will, right? Yeah.
And then you can do
Proof by induction. Do the nth derivative. Right? I'm kind of serious. You could do it. It'd be fun, wouldn't it? You've done the proof by induction.
Where do you get this thing?
Yeah, well, I'm just saying, like, what would the derivative of, like, 3 times 5 to the x be? What would the derivative of that be? Wouldn't that be 3 times 5 to the x ln 5?
yes.
Right, the 3 just kind of comes along for the ride. I'm claiming that the ln 6 is just a constant. Just find the derivative of 6 to the x, which is that. And ln 6 just comes along for the ride, right? It's a constant, right? Just like the 3 came along for the ride. Here, you just need to figure out what the derivative of 6 to the x is.
Okay.
Up here? Yeah. This is equal to 3 times 2 to the x. Right? 3 to the x, 2 to the x. Yeah. Like I said, the algebra is, calculus is where you learn algebra.
Do you use
Yeah.
the product rule for that?
I didn't need to. I mean, if you want to use the product rule, you can. It's just what's the derivative of ln 6? 0.
Oh, okay.
So that other part of the product rule will fall away, but math works, so whatever. Okay. All right, so we'll take a play at it. Isha's book. You ready? So, I don't know, why don't you try it yourself using the technology that Isha is suggesting here?
What is Isha's suggestion?
What I have on the board. Read that.
Oh, that's when you do the differential of y.
But start by rewriting it so that you have e to the x, e to the y, right? And then use the derivative we now know. What's the derivative of e to the y? Right? yeah. What is it? E to the y times dy dx, right? Well, you can say ln e if you like, but that's just 1. And then the derivative of x is 1. So far so good?
Yes.
The derivative of e to the y is e to the y times whatever dy dx is chain rule. And the derivative of x with respect to x is 1. Solving for dy dx gives 1 over e to the y. But if we can write it in terms of x, we prefer that. So what is y again? Oh yeah, ln x. Wait, what?
Wait.
E to the y is just x, we said, right? So yeah, e to the y is x. Well, this is a little bit of an interesting turn here, right? We're saying that 1 over x, we get the derivative of something equals x to the negative first. So in particular, well, do I have it in a box down here? Yeah, there we go. So notice here that we have something that gives the derivative of x to the negative first. We didn't have that when we were thinking about the power rule earlier this year. We didn't have something that yielded that derivative. What's the second derivative of the natural log function? Well, now we jump into the power rule, don't we? Right.
Negative x to the negative 2.
Yeah. I'm so glad you asked, Jack.
Yeah. I have only 4 minutes. November 2017.
Huh? It is on a different page. No. Let's see if we can derive this using the previous result. We're going to use some pre-calc, hack the system. You could use the same technology we just did, but what am I using here from pre-calc?
The natural log rules.
Yeah, the change of base formula. That's what he said, yeah, the change of base formula.
That's what I said.
Jack said it, but it's okay. You remember that rule from pre-calc? Okay. It's a thing we can do. We won't go into it. Now let's just keep in mind, what is this that we're looking at? This is just the derivative of ln x times a constant, right? Isn't 1 over ln a just a constant? So this is us just having to think about what the derivative of ln x is. And then 1 over ln a comes along for the ride, right? That can be factored out of there.
So it's 1 over.
Yeah, then we already have this from the previous page. That's 1 over x.
1 over x ln a.
So let's put it in a box. From here to here, the change in base formula allows you to say the log of base a of x is the log base anything you like of x over the log base that same thing you want over. So this could be, we just chose e to be the base. But in general, the log base change formula says this.
Did you just say cheetah?
Right? Where smiley face is 10 or e or anything you want. So that's the idea there. Again, pre-calculus wins the day, really all day long here, right? Can you do one of these or both before we leave?
Yes.
Is tomorrow's AP problem individual again?
Tomorrow's AP problem is individual.
You have notes?
No.
over x.
Yeah.
Wait, no.
Wait, no, that's wrong.
All right, what do we get here? Derivative of 1 is 0. What's the derivative of ln of 3x?
1 over 3x.
1 over 3x times 3.
So it's
So
just 1 over x again?
1 over x.
Wait. Oh, yeah, this kind of makes sense.
It does actually make sense, again, pre-calculus. The original function can be written as, do you remember the log rules? What's log of 3x? That's the same thing as log of 3 plus log of x, right? So if you did some pre-calculus first, what's the derivative of both of these things? 0. So what is ln of 3x compared to ln x if we look at the graphs? ln of 3x is actually just a vertical shift on the graph of ln x. All right, product rules, there's no, we'll call it quits.
I always
More tomorrow, after the AP product. Have a great day, everybody. Nathan,
Oh, you
glad
remember
you
that story?
stayed.
Laugh right now.
More engaging, right?